All right, so last time we had left off, we had created some formulas in a variety of ways, and I'd given you some caveats about the problems that you might run into with formulas. We're going to look at a few more details with formulas. And the first one is differentiation. MathObjects includes a differentiation macro so that you can automatically differentiate a formula that you have. So, for example, if you have this formula that's a polynomial and you've assigned it to $f, then calling the method d on f, I guess I didn't mention this before, this little arrow, the single-lined arrow, means take an object on the left and use either its method on the right or get data from it, depending on how it's used here. In this case, it's a method. So this day says take f and perform its d method. We've seen a couple of places where there were arrows that had an equal sign instead of a minus sign. That is a double-lined arrow, and that's different. When I see the next one, I'll try to remember to mention that to you. That doesn't mean use a method or a data type. It's a fancy comma, really. It just means pair the thing on the left with the thing on the right. Here we're actually taking f and using its d method. All right, so what this effectively does is differentiates f with respect to the variable x and makes that into g. So g would essentially be this formula, 3 times 2 times x plus 9. For single variable functions, you can put a number here in parentheses after the d, and it will take n derivatives. So you could take a second or third derivative that way. For multivariable functions, you need to specify the variable or variables that you want to differentiate by. So this formula is a formula with x and y, so we need to specify that I want an x partial derivative in this case, or an x derivative followed by a y derivative. So the first one, f sub x, will be the derivative partial f with respect to x, and this second one, fxy, is the second partial with respect to y and x. So those are ways of getting derivatives automatically. Of course, the final results of these are not simplified at all. They're simply, you carry out the standard differentiation rules, and it can get fairly ugly fairly quickly. So they're useful mostly for answer checking, not so much for answer generation or for showing you the results. But you can use them. So one way to try to make things a little prettier is that MathObjects does provide some functionality to make things look better. In particular, because you're generating coefficients randomly frequently, sometimes you'll come up with things that should look a little bit different from just plugging the numbers in. So for example, if I have A is 1 and B is 0 and C is minus 1, and I'm interested in ax plus bx squared plus cx to the third, in this case I'll get 1x plus 0x squared plus minus 1x to the third. And that will not look the way you want. You don't want to see something that has a 0 as its coefficient, and you don't want the 1 to show up. So MathObjects provides a method called reduce that will try to make your equations more pretty by getting rid of those kinds of things. So here the $A, the 1 coefficient has been taken out. The b times x squared is taken out entirely. The 0 times that will be removed. And the plus minus 1 x cubed becomes minus x cubed. So that makes things prettier and allows you to use random coefficients in a little bit easier way. So reduce can be used to try to adjust the results to look a little better. But I want to caution you, MathObjects is not a computer algebra system, and reduce is only there to make formulas more presentable, not to perform algebraic transformations on the formula. It doesn't factor for you or expand for you or simplify for you. It just tries to make things like the plus minuses look better, or zero coefficients look better, or a coefficient of 1 to be not shown. So this reduce idea is there mostly to get rid of issues involved with putting random coefficients in place, but it doesn't make everything perfect, and it doesn't allow you to do important reductions. So Valerio asks, can reduce change e to the x plus 1 to e to the x times e? It's not reduce that will do that. Certainly both of those would be equivalent if you were asked, if a student typed one in or the other for an answer, they would both be marked correct. But reduce won't change one into the other. So reduce does some manipulation, but not a great deal. It's mostly to make things pretty. So it's not a full-fledged algebra system. One of the things that it does do is reduce constants. So constants are combined automatically within a formula, so that if you had something like a was 2 and b was 3, and you did this formula x squared plus a plus bx plus a times b, then you would get out a formula like this without having to use reduce. That is, the constants will get combined automatically. And sometimes that's really helpful, like in this case, so that you don't have to keep an intermediate value for $a plus $b, or $a times $b. You don't need to make separate variables to hold those. They'll get combined automatically. And here's one where a function of a constant will get reduced automatically as well. So if c was 4 and you took square root of c, you'd get 2 as the result. Now, you don't always want this. There are times when you really wanted to not do this. Some of you have run into this already, in particular when there are fractions. So a fraction, if you had 1 over 2, normally that 1 over 2 will be combined into 0.5. And so you might not want that to happen. You can prevent reduction of constants. There are two different constants that are being that are kinds of constant reduction that's being done. One is reducing constants that are added or subtracted, or that have an operator between them, and one is constants that are function calls. And so there are two context flags that control this. Now, flags for the context is a place where, sort of a catch-all, it's where a bunch of properties get stored that don't have any other natural place. So context flags set. Here with a reduce constants. Here's one of those other kind of arrows. It's the double-headed arrow, double-tailed arrow, as opposed to the single one. This says use the set method of the flags object. This simply says reduce constants is associated with the value 0. So this is not a call of any kind. It simply says this thing on the left gets the value on the right. So reduce constants gets turned off, 0, if you do this, and reduce constant functions gets turned off if you do this one. In that case, what you would get is the actual value of A plus the actual value of B and these parentheses, and nothing would be reduced. So you would see the A plus B in the result, and you'd see the A times B in the result here. And square root of 4 would remain square root of 4. It would not turn into 2. So if you want to be keeping the actual structure of the formula and not turning constants into other constants, then you can turn off reduce constants in those two cases. So something like 1/2 will stay as 1/2. Something like 2/4 will stay as 2/4. Something like -3/3 will stay as -3/3. Nothing will get modified. All right. Formulas can be used in other ways. We've talked about using them to produce answers or to produce output for display. You can also use them to compute values using the eval method. So here's a formula, log of x plus 2x, and this says call the eval method on that formula where x is given the value square root of 2. and you'd get y would be the result of f when x is square root of 2. This lets you produce the value of a formula at a particular input. For multivariable functions, you need to specify all the variables that there are. So this x cubed minus 3xy squared, you can evaluate that where x is 2 and y is 3. All right, so that lets you evaluate. Here is another thing you might want to do, which is to substitute a value for one variable but leave the other variable as a variable. So if you want to give some variables a value, use the substitute method instead. For instance, x cubed minus 3xy squared, I can substitute y as 3 and leave x as a variable, and that would set g to be equal essentially to the formula x cubed minus 3 times x times 9, which is what y squared would have been. So that would be equivalent to that expression. You can substitute not just a number into here, but really any type of a value that makes sense in the formula, even other formulas. So if you wanted to let y be x minus 2, you can substitute that into the formula by saying y is the formula x plus 2, and would get essentially x to the third minus 3x times x minus 2 squared. So this is a way of doing some algebraic manipulation on the expression. But again, this is simply a substitution. It's not going to rewrite the formula or factor things out or combine them in any specialized way. This is really for you to use internally in your answer checking as a means of taking a student's formula and substituting something into it, or working with the objects, not really to make a good display of it, but to make something that you can evaluate or use to figure out whether the answers are right or not. But it's not going to necessarily look good after you've done the substitutions. And in our original problem that had the derivative, a function, a derivative, and a derivative at a value, you can see these things being used. So we got a random number here between minus 5 and 5. Here's the original formula, cosine pi x plus x squared. This computes the derivative of that automatically, so I don't need to take that derivative myself. And this says take the derivative and evaluate it where x was the real number between minus 5 and 5 that we got. So I got f df and df at a, and then those get put into the PGML here. You know, the function f was $f, then the derivative is df as the answer, and the derivative at a is df at a. So I don't have to compute, I don't have to by hand work out any of the results here. The derivative gets computed from this formula automatically here, and the value at that derivative gets computed here. So I don't have to write down the derivative myself. I don't have to figure out its value myself. There's a question here, why don't df and df of a have quotation marks? Because these are variables that are storing the answer, not a string that represents the answer. That's the key difference. I've actually got the answer as an object now, so I can pass that object to PGML, and it knows what it is already. No need to turn it into an object. If you've got a quoted string here, that would turn the answer. That would, how do I say this? If I have a quoted string like this, and I were to insert that in the answer blank, after the answer blank, this will get turned into a formula essentially like we did here. Formula will be called on it automatically. But if I've already got a formula, there's no need to have that process occur again. So passing the variable here, I'm passing in essentially this formula already. I don't need to turn it into a math object a second time. If I put quotation marks around this, what will happen is df will stringify itself. That is, it'll turn it into an algebra string that gets stuck inside those quotation marks, and then we'll call formula on it again. Now that would work, but it causes twice as much work to be done. It causes, first of all, the formula that we've already got to be turned into a character string, and then it causes that string to be parsed a second time, which we don't need. So there's no purpose in doing that. It doesn't help in any way, and it just takes it longer to be processed. So since we've already got the object in hand, we might as well use it. Same thing for this one. This one is the real number that is the result of this already as a math object. No need to put quotes around it because first it would have to convert itself into an algebra string, which would just be the number, and then that number will get parsed by the parser into a real object again. And that just does more work than is necessary. All right, so we keep it this way. And those are the things, and I'm glad you asked that. Those are some of the subtleties about quotation marks. Well, you know, I see a lot of people put quotation marks around their variables. There's almost never a reason to do that. If you're putting a variable inside some bigger expression, like if I had $A times x squared here, certainly you put variables into strings that way. But there's almost never a reason to put a single variable inside quotation marks. That's almost never a reason to do that. Almost never. And I'm not going to tell you the reasons why you might. All righty. So again, I'm just about to say more about this here, right here. So string formats. When a math object is used within a string, it automatically generates a string version of itself. So I just talked about that. For example, if we had f was the formula x cubed minus 3x, and we want to use a new formula that involves f, you could do it. You could stick f in here and add 5 to it. And the second formula is essentially x cubed minus 3x plus 5. Note, however, that in most cases, parentheses are inserted automatically. Really, there's parentheses before the x cubed and after this x, so that the expression's meaning will not be altered by the substitution. For example, formula x plus 1 and formula 1 over $f, we want to think of this f as a unit. We want it to be 1 over x plus 1 in parentheses, not 1 over x plus 1, which would happen if you simply did a string substitution here. This is smarter than a string substitution. This is a math object substitution. And the math object knows to put parentheses around itself when it gets inserted into a string so that you actually get its value here correctly represented. 1 over the quantity x plus 1, not 1 over x plus 1. All right. And if you really want the string without the parentheses, you can call the string method to get them without the parentheses. All right, answer checkers. In PGML, you provide an answer checker in braces following each answer blank. We've done that several times already. And PGML converts it to a math object automatically, as I mentioned just a few moments ago. Math objects know how to check student answers against their own values and report appropriate messages. We've talked about the messages. So 3 times x equals 6 is a PGML problem that allows 6 as the answer. Checks to see if the answer is close enough to 6. Well, what does close enough mean in this case? Well, close enough is controlled by the context. And frequently, with an integer, of course, there's no real question about it. But with real numbers, things that involve decimal places or fractions or something like that, what the student types in here is going to depend on how many decimal places they've been keeping track of and so forth. You don't want them to have to keep 17 decimal places. You want them to be able to work with a reasonable number of them. So the answer here is actually not exactly 6, but 6 with a little bit of fuzz. So 6.0001 is actually correct because we're allowing you to be pretty close to 6. So the answer is 6 plus or minus a little bit. And there's a tolerance that says how much of a little bit is it? Well, maybe this is the tolerance. Turns out this one is also correct. Maybe it's a little bit less. Maybe that one is where it fails. Well, that one's still correct. Turns out that this one is incorrect at about this spot. 6.006 is too big, but 6.005 is correct. It's usually about 3 or 4 decimal places that are required unless you change the tolerances. And this allows students to, keep not a huge number of decimal places as they're doing computations. But you can control that. So close enough is something that you can set. The tolerances and what kind of closeness you're talking about are stored in the problem's context. So again, context flags is where this is done, and we can set those flags, and the tolerance value is the value that is used. Normally it's a relative tolerance, which means you take the difference between the correct answer and the student's answer and divide it by the correct answer to get a relative tolerance value, and that's normally 0.0001, which makes it about 4 decimal places that you need to have right. But this one sets not just the tolerance, but the tolerance type, which says absolute. So this one has to be not a relatively close, but absolutely close within this amount, so that the difference between the student and the correct answer has to be within 0.0001 as an absolute value. So that sets the tolerance and tolerance type. Other things that you can set are things like the ranges of the values that you want. We talked about this earlier. Set the variable x so that the limits of the x values are from -1 to 1. That way, when we check a function that has x in it, the values for x will be taken within the range -1 to 1. Normally, the range is -2 to 2, and WeBWorK will ignore any x's that it tries where the function is undefined, up to trying 10 or so times to find points. If it can't find points, if for example, you had the square root of let's see, what would it be, of x minus 1. Suppose you had the square root of x minus 1. On the range from -2 to 2, let's see, do I want that? X minus 1, that would be from x plus 2 to x minus 2. So half of those x values would end up being negative, and half of the time, WeBWorK would try points that weren't defined, and you could run it to places where it doesn't find enough values to test that, and you'll get a little message, WeBWorK can't find enough points to test the formula. So you may need to change the limits to include the places where the function is actually defined. Other things that can go wrong are, for example, places where the function's value is actually equal to 0. These are places where relative tolerance breaks down. Remember that relative tolerance is the absolute value of the difference between the student's answer and the correct answer divided by the correct answer. And if the correct answer is 0, we can't do that division. And so the closer you get with the correct answer to 0, the worse relative tolerance gets to be. And so places where the function's value is 0 is places where the numeric properties that we're using to test these things break down. So you want to avoid places where the function is 0. So you may need to change the limits in order to avoid those as well. All right. So overriding the context, let me make this a little bigger. So drop over. All right. So it's possible to override the values in the context for individual questions by setting values in the math object itself. And this can be done with the method called with. So suppose I made x to be the real number pi over 6, and I want the tolerances to this to be absolute tolerances. Well, I can use with and add to it tolerance and tol type to make these things be set on the variable x itself rather than in the context. All the other variables in the problem would have the context tolerance and tol type, but this one would have these specific ones. So this overrides the context tolerance. Well, here, if I take a formula of, say, square root of x minus 10, if x is between 2 and -2, this is never defined on those x values. So I want to change the limits to be 10 to 11 here so that I get values where the square root's defined. So this would say a formula with limits being 10 to 11. So those are the things you might need to do with depending on the formulas you're using. How are the context flags looked up? When a math object looks up its context flag, it does it in the following order. First, it looks to see if it's been set on the object itself, like we just did with the with command. If it's not there, it looks in the formula that generated the object. So if the object is a number that came out of evaluating a formula, it looks back at the formula to see whether its tolerances were set, for example. So that if you are using a formula and getting values out of it, you can set the tolerances on the formula itself. If it's not in the formula, it checks the answer checker that's in effect if an answer is being checked. And if it's not there, it looks in the context. So there's a hierarchy where these things get found. And note that the context checked is the context in which the object was created. Somebody asked about, can you have more than one context in a problem? And yes, you can. When a context has been set and you create a variable in that context, that is, whatever the active context is when you create a math object, that math object remembers that context. And if you later change that context to a different one in the problem and create new variables, the one that you created earlier keeps its context. So if you had an interval, for example, in the interval context, and you later changed to the complex context, both of the objects you created would know what context they came from, and there would be no problem using both of them in the same question. So that means you can just create an object, change its context, create an object, change the context, create another object, and still get answer checkers for the two that work correctly. All right, so how do you get answer checkers? Well, PGML does this for you, but you can also obtain the answer checker directly from a math object by calling its CMP, its compare function. So if we have a formula like x squared plus x minus 3, I can get an answer checker for that formula by calling CMP, and I can store that answer checker as a variable. And then I can pass that answer checker on to PGML by simply giving it the answer checker. So a lot of different things can go into the spot after an answer blank. It could be a number. It could be a string that contains the answer. It could be a variable that contains a math object that is the answer. It could be a answer checker, like the one that we've got here in comp. So a lot of things can go here, and they should do the thing you naturally think of. And this will check for the answer that the CMP came from. So it's an answer checker for this function f. Now you may say, why would you ever want to do that? Well, the reason is that there are flags that you can set on the answer checker itself that control the action of the answer checker. So in this example, we compute a value 1 plus square root of 5 over 2, and we get an answer checker that has the tolerance set and pass that answer checker on here. So that sets the tolerance. So this is another way to set the tolerance. We could have set it on the context itself. We could have set it on the object A, or we could set it in the answer checker. So this is the third line of that hierarchy I had a couple of slides back, where we got the current answer checker. And there are some special flags on answer checkers that are not available anywhere else. So you might need to do this. So here is an example of doing this. Most math object answer checkers have options that control how the check is performed, in particular what type of error messages are produced. And these are passed to CMP as flags. So here is, for example, a point, 1, 2, 3. I'm getting its answer checker, and I'm saying don't show any coordinate hints and don't show any dimension hints. And if I put that into a variable, I can pass that variable on to PGML. And here's a vector object that says parallel is 1, which means that this answer checker will accept not just 1, 2, 3, but any vector, any non-zero vector that's parallel to that vector. So here are the results of say, the point checker with hints and without hints, and this vector checker with a parallel set. So with hints, if I say 1, 2, this should say the number of coordinates is incorrect. Whereas if I've said coordinate hints are 0, this one will not give me such hints. So this one will silently mark this incorrect and not tell me anything more about that. Sorry, that's the dimension is wrong. If I had an incorrect coordinate, like 4, if I'm getting coordinate hints, that will say the third coordinate is incorrect, whereas the one with coordinate hints set to 0 will silently mark it incorrect. So you can control the error messages in the answer checker itself by setting these kinds of flags. The dimension hints was the first one I did that said too few or too many coordinates. Coordinate hints say which ones are correct or not. This guy about parallel, this is looking for the vector 1, 2, 3. That should be correct. But any multiple of that should also be correct. So 2, 4, 6 should also be right. That's correct. Or 1, 2, 3, I could take twice it, 2 times that vector. That's correct. Or say the negative of that vector. That's correct. And so forth. The only one like that that won't be should be 0, 0, 0. Should not be allowed here if I'm lucky. Incorrect. All right? So that allows you to specify a direction without worrying about its length. So those are reasons to get the answer checker by hand, rather than letting PGML do it for you. So most of the hint type options take their default settings from the value of a particular variable called show partial correct answers. We may have seen this in a problem at one point. So if you have show correct answers equals 0 anywhere in your problem, it doesn't have to be before the answer is produced, anywhere, then this would also turn off the coordinate and dimension hints, even though they have not been disabled explicitly. There are other options that you can put into the answer checkers. Those are listed at this link on the documentation in the wiki if you want to check them down. And they vary depending on the type of the object. So, for example, vectors have this parallel option, whereas points do not. Okay, so compute and the correct answer. What is this talking about? For a constant value like the real square root of 2, the correct answer is the decimal value, such as 1.4142, whatever, whatever. And that is how it is shown when the student views correct answers. If you want the correct answer to look like square root of 2 rather than 1.414, use compute instead. So there's a difference between saying compute square root of 2 and real square root of 2. And they are in how the answer is displayed. The checking is the same, but it's the display of the correct answer that's changed here. So instead of this, compute sets the correct answer to be the actual string that you did, appropriately techified. So square root of 2 is what you would see if we ask for correct answers. And we look at both of these. One of them will say 1.414. The other one will say square root of 2. So the one that was real square root of 2 shows the number. The one that was compute square root of 2 shows the square root of 2 as the string. So there's a difference between those. That's the other reason to use compute that I mentioned in an earlier slide. I said compute had a second feature to it. The second feature is that it sets the correct answer to be the actual string that you used to display the number. So if I had the one that was 1 plus square root of 5 over 2, it will show up as 1 plus square root of 5 over 2 rather than the 1.6 whatever it is that you would get out of that. So compute has two purposes. One, it changes the string into the math object, and two, it sets the correct answer to be exactly what you typed in the string rather than the resulting value. All right, so that's an important one to know about. All right, some answers ask for a numeric result such as a word, ask for a numeric result or a word. That is, you might say, what x values is this function undefined? And they could be that the function is always defined. So the student will either enter x values as a list of comma-separated list of values or the word none. And you need to tell them to do that. So in that case, where the string is an answer, where the answer is a string, the checker will not be able to do the usual type checking that produces the error messages that you want, since it won't know what other type of answer would have been expected. If you simply say that this is the string none, it doesn't know whether what you were asking for was a set of points, or whether what you were asking for was an interval, whether it was asking for was a list of numbers, or what. So you need to give it a little more help and tell it what type of answer the student might have entered here instead. So to do that, you use the type match option to tell the checker what you were looking for. So here is string none, its answer checker, where type match is set to be value complex. This is saying I'm asking for a complex number here. So either the string or a complex number, none. So this will report errors like those for a complex number, so that if the person types in a point, you'll get the message, your answer isn't a complex number, it looks like a point. Whereas if you left this out, it would say your answer isn't a string, it looks like a complex number, which would give away the answer, that the answer is none. So you want to use these to give hints, particularly in the case where your answers are strings. So that's an important subtlety. For there's also another thing we talked about when I said some functions are near zero and you want to avoid that. Sometimes if you've used a problem and you get that kind of situation, what will happen is the student will get will type in a correct answer, but it will be marked incorrect. And they'll come to you and say, my answer is right, I know it's right, and I think WeBWorK is wrong. Most of the time, the student is incorrect, they've done something wrong, but sometimes they're actually right, and the question is incorrectly marking them wrong when they shouldn't be. And if you want to try to track down what's going on there, one of the ways to do that for a formula is to use the diagnostics option. And you do that by saying the formula I've got answer around this. Ignore that. It's old slide. You put the diagnostics 1. So if you took this as your answer checker, what this is going to do is turn on a special diagnostic mode so that when you type in an answer, you're going to get a lot of information about that answer. Now, you do not want this in a live problem that students are using, but as you're testing it, you can do this. So suppose I typed in my answer, x squared, and I had 2.001x plus 1.00001, or something like this. So here's a formula that's close to this. And we could find out, I don't know if this is going to be marked right. Okay, this is marked incorrect. Excellent. That's what I wanted to see. And down below here is a lot of information about the checking that the math objects were actually doing to find this out. So you'll see, first of all, 3 graphs. The first one is the graph of the correct answer in green and the student answer in red. Well, the green one is hidden by the red one. They're so close together that you can't see the difference in this graph. The second graph is the absolute error between the two. So this is the difference between the student answer and the correct answer. And so you can see that these go down. They're equal at the origin, and then they differ again more as you go off to the sides. Not quite equal at the origin, slightly off, but very close. And so they get worse. This green line is the cutoff that the tolerance says if the tolerance type was absolute error. And this is the relative error here. So the red graph is the student's relative error, and the green line is the cutoff for that. And what you see is that the relative error is very small, except near this point. And that's the point where the function is 0. And that is, as we get smaller and smaller values of our function, the relative error spikes because we're dividing essentially by numbers close to 0. And so this function, because the original function goes to 0 here, the relative error blows up here. And it turns out that one of the test points we've got is in a spot where the relative error is reasonably large because it's close to that point where the function is 0. So the relative error is unusually large. These are the x values that were actually used in the problem, minus 1.92 and so forth, and those are marked on the function with these points. The correct answer and what its value was, the student answer and what its value was, the absolute error here, and the relative error, which is the one that's being used, and these are marked green for okay and red for not okay. So 2 of these had relative error that were larger than the cutoff value, and that's mostly because we're allowing values where the function is close to 0. So one way around this would be to adjust the limits of the function to being something that doesn't include that 0. If we kept away from that 0, the relative error will be under control, and we won't get these points that are unexpectedly bad, because they're not particularly bad. This function really ought to have been counted as correct, but because of how relative error works, it blows up at part of the function that we actually are caring about. So we want not to care about that part of the function. And even though this is just a polynomial here, and you would think there can't be anything numerically bad about this function, there really is. And that's the zeros of the function. And that one of the zeros of this function is within our minus 2 to 2 default range. And so we ought to change the limits of that function to avoid that 0. Of course, if the coefficients of this function are randomly chosen, the limits are going to depend on those coefficients, and it can be quite difficult to actually choose them accurately. But this tool can help you find what's going on and what's really at stake here. And you can see immediately which points are the ones that are causing trouble, and there it is, the spike in the relative error that's at fault. All right? So that's useful to know. You put this in temporarily in an editor where you're editing a local copy of it, not the one that students are using. Run that and see how it works, and then take it out again so you don't accidentally save it into the official copy of it. All right? And I know Gavin uses this quite a bit, as almost every problem he's sent to me that says, this problem isn't working, turns out to be a numerics instability of that kind. All right. Fuzzy checks. More about this fuzzy check stuff. This idea of being close enough is pretty straightforward for a real number. It means that you're, within a certain relative distance of it. But what does it mean for a complex number or a vector answer? There were several ways this could have been done, but in general, in MathObjects, it means to do a close enough check in each coordinate separately. And that means that it works reasonably well as long as the coordinates aren't 0 or close to 0. Because if they're close to 0, you run into this relative error problem. Now, to avoid that relative error problem, actually division by 0, WeBWorK uses what's called a zero tolerance. And if the values are small enough, it switches from relative to absolute tolerances. And so this 0 in this vector is actually being done as an absolute tolerance using a separate set of tolerances called the zero level tolerances. So I could put in here a number like minus 2.0001. If I put 0001 there and 1.0001, this should be close enough in some senses, but it will be marked incorrect because it says the second coordinate is incorrect. Because as an answer close to 0, this 0.0001 is not close enough. It has switched to an absolute tolerance that's different from the relative tolerances that are used everywhere else. And in fact, you've got to get really, really close to 0 to do this. I don't even think this is close enough yet. 1 to the 10 to the minus 10th. It's not. You've actually got to get down to 12 or 13 powers of 10 to get it close enough to 0 to count. So that's another situation where answers that are correct can be marked incorrect because of the zero level tolerances. Again, relative tolerance issues. You could switch this to be using absolute tolerances in this case, in which case that 0.0001 might have been enough. But watch out for zeros. Zeros are a real problem for relative tolerances, even if they look nice in your problems. So be careful of that. Be aware that 0 is an issue as you design your problems. Okay, fuzzy reals. The fuzzy checking has been incorporated into the overloaded equality and inequality checks. Like in your Perl programs, when you check for equality, you use a double equal sign. $A equal $B is the test to see if A equals B. And in Perl, for real numbers, those would only be equal if they were actually exactly the same internal representations. But that's not what we want when we're checking, for example, a student answer. We want these relative tolerance fuzzy checks. And so these are built into these operations in your Perl code. MathObjects has overloaded those operators to give the fuzzy checks. So that means if you say A is a real number 10, and I check if A is 10.0001, set B to yes, otherwise set B to no, B will be set to yes, because under the normal tolerances, this is too small to worry about. So 10.0001 is equal to 10 as far as WeBWorK is concerned. So these ones will get you B to yes. And if you use these operators inside your answer checking, this will do exactly the way WeBWorK tests them. So you don't have to worry about doing relative testing yourself. You simply use the equalities, and they carry out the same checks that WeBWorK is going to do. That has what you might think of as an unexpected consequence, which means that inequalities also are fuzzy. So if you say A is real 10 and ask, is A less than 10.001, the answer is no. Why is that the case? It's because A equals 10.0001. You do not want two of these to be true at the same time. So less than, equality, and greater than should be mutually exclusive. And so if it's equal, it can't also be less. So all of these things are fuzzy. So less than or equal to would be true here because it is equal to it. But it's not less than. As an actual real number, it is, but as a fuzzy real, it's not. So watch out for these things. You do not want to have these things overlap. If they did overlap, then the negations would not be mutually exclusive either. So if you said A was less than some number, and you changed that to being it's not the case that A is bigger than or equal to some number, you might not have changed the result. So these have to be mutually exclusive in order to have logic work the way you expect it to. So watch out for that as part of what you have in your head as dealing with these fuzzy real numbers. Fuzzy real numbers are fuzzy. You need to take into the fact that it's within a certain range of the number you're talking about, and A is not less than 10.01. It's equal to 10.001. Comparisons. Again, these comparisons are overloaded, and you can use these not just on real numbers, but on any type of math object. So that means you can check for formulas for equality as easily as you can for real numbers. So you could say, is this formula equal to this formula? And in your program, the answer would be yes, those are equal. Because as functions, those produce the same values. And these two vectors would not be equal. You don't have to go through and check it yourself, coordinate by coordinate. MathObjects do that for you. So the equality operators have been set up to work with MathObjects so that they compare themselves in the same way that student answers are compared to correct answers. So you can use these checks in the same way that student answers and correct answers are checked. Turns out to be very powerful. All right, the MathObject library is documented on the WeBWorK wiki. Here are links to the various important pages. Introduction to MathObjects, context, all the different MathObject classes that are built in, answer checkers, and so forth. custom answer checkers, how to modify the contexts. So people who want to know how to add and remove operators and functions can use that. And the documentation for the various macro files available at this link. So these are important places for information. The next set of slides are example problems. I'm going to run through these fairly quickly, but they're here for your reference. And there's 2 pages for each, one that says what is the problem and then notes about that. So this is going to be a problem like this is the first one we talked about, a function, a formula, its derivative at a randomly chosen value. And I've added one more thing, which is the tangent line to the graph of f at this point is given by y equals such and such. You can look at the problem source, see how it's done. We create the random point. We create the function. We create the derivative. We evaluate the function at the point. We get the derivative. We get the derivative at the point. And we set up the tangent line to be the derivative times the x change plus the y value at that point, and reduce to get rid of pluses or minuses and coefficients of zeros and so forth. So that makes it pretty. Then you lay out the problem and you include the various results as your answers. And that's all there is to it. Again, all of the work is being done in some sense by MathObjects, by simply setting up and evaluating the functions at the right places. The notes on this say you don't need to specify the function in one form. Eval evaluates the function. Derivative is taken automatically. Reduce fixes up problems. So here are a bunch of other problems that work similarly. Here's a vector-valued function that's essentially the same. The only issue here is that now the formula is vector-valued, and the point we get out of here is actually a point, and we force it to be a point so it's not a vector. And L is given parametrically as point plus t times a vector. The f of a is now a vector value. The derivative is a vector. Evaluate that derivative at a point. We have a constant vector times t plus a constant point. So this is now a parametric line. There's a special parametric line answer checker, which we have included here, that will check even if you've used a different point or a different vector to create this. So there are specialized contexts like this that will test specialized situations. So a parametric line is a one that will do this regardless of the direction and the point that you used here, as long as they produce the same line, even if it's parameterized differently. So that we'll talk about that here. Here is one that talks about intervals and sets and how to deal with them. I'll let you play with that. Here's one with matrices in it. So this particular one, oops, sorry, didn't mean to do that. I wanted to look at the source. This one creates a matrix using random values in its 2x2 matrix, random values in its rows. It creates a matrix that's the square of that matrix by simply taking the original matrix and squaring it. It makes a column vector with using a special function for non-zero vector 2D. That's in the parser vector utils macro package. Makes it a column vector so that it prints vertically, and then computes n times v. Then it uses those things in the answers. The only thing of any interest is the star after this, which causes the answers to be laid out as an array where you type in individual entries in the matrix. So that gives you these 4 things instead of one blank where you have to type the entire matrix yourself. So this says compute the values that go in these spots or multiply this stuff out. So we could type those answers in there. This talks about that. Here's one that uses complex numbers. There's really nothing surprising here. It's very much the same problem as before, except we've got z is now a random number plus a non-zero random number times I, so that we have an actual complex number here. Our formula is written in terms of z, which is a complex number, and we can evaluate that at our complex number. So the layout of this problem is identical to the other one. The only difference is our value z is complex now instead of real. Complex numbers. Here's an interesting one. This says, find a vector that is 45-degree angle with this vector. And again, this is any vector that's that one. So there are a lot of possible answers for this one. What would be an answer to this? I don't want to figure it out by hand, so let me find the answer. All right, minus 4 is 0. All right, so minus 4 is 0 is such an answer. So that's correct. So is that right? So the dot product of this, 45-degree angle, right. Yeah, sure. So this is at a 45-degree angle, and this one is horizontal. So, we're golden there. All right, so how does this work? This one uses what's called a custom checker. Paul, I think, is going to talk more about this stuff next time, but I just want to give you a flavor for it. Here we have a non-zero vector, 2D, and I've made an overline V so I can show you V with the overline here. I create a new vector that is perpendicular to this vector. I find the coordinates of this vector. Someone asked about how do you get the coordinates of a vector. The value method says, give me the data for this object, whatever it is. And in the case of a vector, it's the coordinates. This says, break up that array into the two values, A and B. And I make a new vector that's minus BA, so that's a vector perpendicular to this one, and I'm calling that U. And I set a new vector that is U plus V over 2. So this is a vector that is halfway between U and V, so that's at a 45-degree angle. Since these are 90-degree angles, over 2 is not really necessary, but it's a vector that's partway between. And we get an answer checker that's Q's answer checker, but I'm going to make a special, I'm going to override the action of this checker with my own subroutine. And what does this subroutine do? Well, it gets the correct answer and the student answer out of what got passed to it. This is a special array, which is all of the things that got passed to my checker. And the checker gets the correct and the student answer. And what I'm going to simply do is take the unit vector in the correct direction and the unit vector from the student and take their dot product and see if that is the cosine of pi over 4. Remember, the dot product the dot product is related to the cosine. And in terms of unit vectors, it is the cosine of the angle between them. So I check to see if that's the correct angle. So that simply tests whether these are correct or not. And if this is true, we're returning true. And if it's false, we're returning false. And the checker says, is this the correct answer or not, by returning true or false. So we've got a custom checker here that we can override the action of the normal checker. We still get all of the type checking that the checker normally would do, and our checker is only run exactly when the student's answer has the right number of coordinates and is a vector. So we don't have to worry about any of the overhead of is this answer of the right type? Is it the right kind of a thing? We simply check it against the correct answer, and all of the difficult work is done by the MathObjects, and all we have to do is implement the actual check we care about. I've turned off answer coordinate hints here because for this case, it doesn't make sense to say your first coordinate is wrong because it has an infinite number of these things, and your first coordinate will have a second coordinate that goes with it that would be correct. So coordinate hints are turned off. We do actually have what we consider a correct answer here with Q. So it has coordinates. We've got an example of a correct answer because we have to give the student a correct answer, an answer that we agree is right. So we produce a correct answer and check it against, so that will be the one that gets shown, but all of the other possibilities would be allowed. So if I took a different one here, say, 8, 0, this would also be correct. or should be. No, not minus 8, 0 would work. So that would be correct. Something that's a multiple of that one, or one of the ones that is in the other. The vertical ones should work. Vertical ones for this would also work. So 0, 8 should work. Yeah, like that. So these ones now are allowing lots of different possible answers. So somebody had asked earlier, how would you check if it was a unit vector in one direction or the unit vector in the other direction? You would use a custom checker like this, where you would do the check in here that says, is it the one positive one, and is it the one that's negative? So you can make your own checking that only has to deal with the actual case that you care about, not all the possible weirdo things the student might have typed. Things to note. Yes, okay. This one is an answer that, this is one of my favorite kinds. Show that the function blah, blah, blah is not one-to-one by finding two distinct values, x1 and x2, where the function's values are equal on those x1 and x2. Well, this is not a question that you can check, is x1 a correct answer, without knowing x2. These two answers are tied together. You can't check one without the other. So this is one where you have to know both answer blanks and what's in them before you can actually tell whether either one of them is correct. And this uses a special macro file called multi-answer. You create a multi-answer object that has the two values you care about in them, and you use the with thing to set some values on it, and one of them is a checker for it. And the subroutine in this case gets the correct answers and the student answers as arrays. I pull off the student answers as x1 and x2 from the array. This dereferences an array pointer. Again, these are very technical things. I'm not trying to go through all the details here, and you're not necessarily supposed to be able to reproduce this, but I want to give you the idea of what's happening. We get an array of correct answers, an array of student answers. I grab the individual student answers. I evaluate the function that I cared about, the one that I've defined up here, at the two student answers. I do this using parser evaluate so that if there's an error, if the student value, and there isn't going to be in this function because it's defined at every point, but if you had something with a square root and the student's answer was a place where the function was not defined, your checker would fail because you would get a on division by 0 or a square root of a negative or something. So this prevents failures, and it sets up a message, I can't evaluate the function if we didn't get a defined answer for it. So this lets you trap errors. So I'm trying to just show you that you have a lot of control here. Not all the details, but you don't have to worry about it. And here it says your two values must be distinct if the two are the same, so they can't get away by typing the same x value to both. You have to be careful about that. And then we return that's true if both are defined and if the function's values are the same and the two are not the same points. So that tells when the answer is correct. The way you use this in PGML is you've set up this multi-answer object. It used to be called multi-part, which is why I always use MP for it. And you just pass MP into all of the answer blanks that are going to be used by that multi-answer checker. And that's it. So it will get you the answers that are in those two, passing you them into this student array. So here we can find values that do this. 0 and what would we get here? 0 would give us -3. So we want square root of 3 here, square root of 3 as another one. So those two are correct. But you could use, there are certainly other values that you could have used there. It's like minus square root of 3 should do this as well. Isn't that right? Minus square root of 3. Minus square root of 3, I think also will do this because you get minus here, but the second one will be plus, and they'll cancel each other out. So there's another one that's correct. So there are a variety of answers that can show up for that. I think that's the last one in the list. This is then the two labs, again, show up here that you could take a quick look at. All right, so I'm going to stop there for a moment before we go on to PGML again and see if there are questions. So what are questions that I've missed? Can you give feedback for the case student only types one of the two values? Normally your checker is not called unless all of the values are filled in, but you can set a parameter. I didn't show you all the things that were in this previous. I didn't show you all of these other things that are being set here, these other kind of things. And there's parameters like this that say you want to get to check answers even if one is empty. So you can do that, but then your checker has to be a little bit more sophisticated because you have to actually decide whether they've typed an answer or not. You can do it. I will say that this one says single result. That says that when I type these in, if I type 3 into whatever, what it's doing is having only one line rather than two. Normally there would be two answer blanks. There would be two rows. But here I've combined the two. So these two are both part of the same, and that's being done because this says single result. If that were 0, you'd get a separate line for each. And these things are saying, how do I want to combine the two? So we put the word and in between the two, and in tech we put an H box and between the two. So you can format the results that way. So if you want them to have commas or other kind of things between them. What is the difference between this and extract? Okay, Paul asked about the vector value and extract. The value method returns all of the coordinates as an array. Extract says give me one or another of them. Extract with you have to pass an index, and so extract 1 would get you the first coordinate, extract 2 would get you the second coordinate, and so forth.
David, there was a question earlier that came up, which is, suppose you can define different variables either in different contexts or by calling them with the with method to set a different tolerance. And then the question was, suppose you then ask for a combination of those as your solution to an answer. So if you have x defined with one tolerance and y with another, you ask for the solution, which is x times y. How is the tolerance set for that?
The first of the two is the one that controls what's going on. So if you use two, well, first of all, if they're formulas, you actually won't be able to combine them. Formulas have to be from the same context when they get combined, I think. Maybe that's just for comparison, but normally if you've got two things from different contexts and you combine them, the first one's context is the one that gets used. And so values will get copied from the first one into the result, and that will control it. So if there's a tolerance set on the first one, that will get copied into the result, and that tolerance will be what's used.
That clears things up nicely.
Okay. This is also important for things like comparisons, for equality comparisons and so forth. It's the left-hand one that controls it, so that if you're comparing a function to another function, the points at which the functions are evaluated are controlled by the first formula. So that if, for example, the first formula is undefined at some values, those values points will never get used because the first one is the one who chooses the points. And then the second one gets evaluated at those points. So that if, for example, you're interested in the difference between log of x and log of absolute value of x, you want to be careful about which one is on the left. And so MathObjects always puts the correct answer on the left and the student answer on the right. And if you write your own custom checkers, you should do that too, because it's the correct answer whose domain you really want to use. So that, for example, log of x will never use a negative value, whereas log of absolute value of x could. So if you had log of x on the left, it will equal log of absolute value of x on the right, always. If you switch that order, it may sometimes be equal and sometimes not equal. Because if you happen to choose points, all the points that are positive with a log of absolute value of x, which is possible, randomly chosen values can all be positive, then the two would be equal. But if you had a negative value, because log of absolute value of x it allows that, it would not match log of x because the negative value is undefined over on the right. So the order in these things can matter, and you want to keep that in mind. Always check correct answer on the left and student answer on the right. Subtleties. These are all very subtle things.